But some of the examples in your homework are easier than this. One of your homework problems is about an exponential. Like, if you're trying to bound the derivative of an exponential, this doesn't happen, right? It's an exponential, so the derivative is an exponential, and so the bound is much easier to think about. Here we had to work a little bit to find the m. But now, if I haven't made some stupid mistake, though, what does this tell us? We have an error in trapezoid rule of order 6 that is at most what? One over what? 3 times 36, which is what? 108? So let's see here. If we look at that, then these things are multiplicative. So if I do like 4 times the integral, right? 4 times the integral from 0 to 1 of dx over 1 plus x squared, this should be approximately equal to pi, right? So I think that this would imply that the error, if I do, if I do 4 times the trapezoid rule of order 6 for this integral, it should be that minus pi should be what? Less than, the error should be less than 4 over 108, if I've thought through this correctly. All right, let's try it out. Yeah, see, I just happened to be reading this thing about the integral of secant earlier, so it's on my brain. They're asking a harder question. How do you motivate this integral? I have no earthly idea. Yes, sir?
I was wondering, how did you get 0 to 1 for the integral?
That was given in the problem. But you see why it would be given is because we know that the integral antiderivative of that's inverse tangent. And so that gives us a connection to pi. You could in principle use this integral, 4 times this integral from 0 to 1 of dx over 1 plus x squared. You could in principle use this as a definition of pi. Right? In principle, you could make that, the question is, how do you define pi? Is it the ratio of the circumference by the diameter, right? It's harder to calculate that directly, right? Well, unless you're in ancient Greek and you got a lot of time on your hands, right? And you keep looking at rational, these inscribed polygons, do better and better. But this is just, you see, this is very nice because we can calculate this to whatever accuracy our heart desires. Now that if you have proved that theorem carefully. Yes, sir.
Did you do for, like in the red there, you got 2 times 2 over 1?
What I did, yeah, I know that's a sneaky step. I replaced the numerator with the largest thing. Really, I want to look at, I don't think I even need absolute value bar, but generally speaking, you could simplify your life by putting absolute value bars. We're actually looking for a bound on the absolute value of the derivative. So if it happened to be like minus 30, if the second derivative happened to be between minus 30 and 2, m would be 30. That's not really an issue here. This function is increasing. No, wait a minute. Well, the function's decreasing, but on the other hand, it looks something like this, so it's always concave. Let me stop talking. You just had a simple question. So here, the reason is this is at most 2, and this is smallest 1, and so that's the largest fraction possible. Okay, now for this homework, guys, I do not expect you to take a piece of paper out and write out Simpson's rule or trapezoid rule of order 10 or something. I'm totally cool with you using the website and saying, I used this website and I found S6 was blah. I found T whatever was blah. The things I will expect you to be able to do on the test, perhaps, is actually apply these theorems to interesting questions. That would be the question. I won't actually waste your time to calculate Simpson's rule, for some explicit. I mean, it would take you 10 minutes, and I would have to take points off because you said 1 + 1 was 3 somewhere, and then we would all be sad. Okay, so let's see here. You're like, but that's easy. What you just said is on the test is harder. Okay, fine, you got me. It's true. I sent you a link to this thing. Oh, shnikes. How can we get interval width? I don't want interval width. I want number of... Oh, and I don't want Simpson's rule either, do I? Let's see. If I want... How many... Will it take... I don't know. I'm not... We're supposed to do trapezoid rule order 6, right? So let's see if it'll take this. Calculating. All right, so here's Simpson's rule, which we don't care about, right? I mean, you can care if you want, but the thing that's cool down here, you notice, although I'm slightly concerned that this really is the genuine trapezoid rule. It should be, if the interval width is 1/6, that should be trapezoid rule with order 6, right? This one here. And so it works out to so T6 apparently is what? It's equal to 0.784241. And so let's see here. I wanted to actually just calculate 4 times that because that's more interesting. So what's 4 times? 4 times T6 is what? What's 4 times 0.78? Thank you. What? But I got maybe it's what you said, 3.1, 3.1369, 64. Now, if you subtract pi from that, assuming that the calculator is not evil and isn't lying to us, so if I look at the absolute value of 4t6 minus pi, I get come on. Oh, stupid scientific notation. Let me think for a second here. 0.0046, well, basically 46. I'll stop there. As you can see, 4 divided by 0.8, 4 divided by 108 is what? 0.037. As you can see, we are well within the tolerance that is suggested by the theorem. Now, the reason that the answer is actually closer, the approximation is closer to the answer than the error estimate is because I didn't use the strict form of the error estimate actually says that the error is equal to this thing with m replaced with the fourth derivative at some particular c between a and b. And the error is actually equal to this with the second derivative actually at some c between a and b. So if you could actually find that c, you could attain that precise error. But who cares? What we're really after is just some kind of idea of how close are we to the truth. And see, this says that if we use 4 times this integral as a way of defining pi, then if we calculate the trapezoid rule of order 6, we're going to be within 0.03 in terms of the absolute value of pi. Now you could take this and divide by the experimental or the theoretical value of pi to get like a percent difference and stuff like that. But you know, we'll just look at absolute error in here for now at least. Does that make sense? I mean, this is kind of scary, right? I think this is kind of scary personally. I was scared I wouldn't be able to find this today because I haven't worked it out before. It's always kind of dicey. But oh well. All right, there's another class of problems that I should try to talk to you about how to set up. I don't know if we have time to do one of those today, though. Probably not. Oh, definitely not. So the other kind of problem is it's just a little bit different. So like here's the other problem type would be suppose you're trying to approximate an integral, right, to a given accuracy. Like so you want to make the error smaller than a certain value. Then the question to ask is what n do I need to get to in order to make sure that my approximation is within 0.1 of the actual integral or whatever. So that's kind of a different question, right? Here I gave you n and we just calculated the error, we compared. You see what the difference would be? Here's the integral, here's the error I want to not have larger than, and then the question is what n suffices for a given method. So I'll try to work one of those tomorrow. You have a few homework questions like that in 8.7. Like homework number... More? Well, anyway, we'll talk about it tomorrow. Thanks, guys. I might get to that in the later section if you want to look at the video later, if you're interested.